So in 6.2, we did these volumes. We spent 2 class periods looking at volumes, mostly volumes of the solids of revolution, where you take a curve, revolve it around an axis, and end up with a volume. And the nice, convenient trick to finding those volumes is to find a formula for the area of the cross-section and integrate over the range of all possible cross-sections. So if you can do that, then you've got a volume. But it turns out there are certain areas, when revolved about a particular axis, result in a volume that cannot be easily computed using our disks and our washers. So there is another technique we're going to introduce called volumes by cylindrical shells. And to illustrate the problem, I wanted to look at an example real quick first. We're going to find the volume of the solid that's obtained by rotating about the y-axis, a region bounded by y equals 0, and the curve 2x squared minus x cubed. All right, so I'm going to draw this picture for you, which we can, again, if you're working on this on your homework, you go to your graphing calculator or Wolfram Alpha to graph something like this. I've done that in advance, and the shape of the curve looks something like this, like a parabola, and it turns around and goes like that. Now again, we're going to revolve this thing about the y-axis. So I'm going to go around this axis here, which means I would want to mirror image this thing as best I can. Right, and then you've got to make this bowl-looking thing. Okay. Remember that whenever you do the process of finding that volume, since we're revolving about the y-axis, I'm going to pick a y value, and then I'm going to go out to the curve and see that it extends from here to here. Okay? So, again, think of this as though you were looking down on it. You rotate it up to yourself, you're going to see this circle with a circle inside. Okay? This right here, this distance right here represents the outer radius. And this distance in here, that is from here out to there, is the inner radius. The problem now is the outer and the inner radius are both from the same function. Instead of an f on the outside and a g on the inside, you're going from one part of one function to the other part of another function. Okay? And technically that means it's not even a function. Right? Whenever you do a function, it has to pass what's called a well-defined definition. Now when you do functions of x, right? Functions of x, you have what's called a vertical line test. And the vertical line test means it can only hit the curve at each place once. Now we're doing horizontal, right? To be a function, you'd have to pass a horizontal line test. That's for functions of x. This is for functions of y, right? My claim is this guy you're looking at right there is not even a function of y, because it has 2 outputs for a given y. Okay? So you have a problem. That is, you're going from one function to the other. Okay? So what we do is we need a new method. Because we can't write the area as the area of the outer circle minus the area of the inner circle, because we don't have a function for the outer radius and a function for the inner radius. They're both the same function. Okay? So finding a formula for that is going to be tedious and painful. So we introduce a new method called volumes by cylindrical shells. Instead of using cross-sectional disks, we're now going to do cylindrical shells. And I went ahead and threw some pictures in here to give you an idea of what we're building up to. So let's think of this particular curve that I have right here on the left. It's in the blue on your screen. I know your handouts are black and white, but this blue area right here, I'm going to revolve around the y-axis. And in revolving around the y-axis, it's going to create a shape that looks like that area on the right. Okay? Taking y equals f of x, I'm going to revolve it around the y-axis. Now, instead of taking cross-sections by picking a y and slicing it horizontally, what I'm going to do is I'm going to pick x values between A and B, like is being done down here in this picture right there. And at a given x, like this xi right there, I'm going to find this cylindrical shell. It's a cylinder, but it's a cylinder with a hole inside of it, right? I'm going to find the volume of that shell. And then I'm going to find the volume of a whole bunch of shells, 3, 4, 5 shells, okay? By finding their height and making them all the same width, and then add up the volumes of those shells, which should be a pretty easy formula to come up with, because the volume of a cylinder we know, and so the volume of a shell would be the outer cylinder minus the inner cylinder, right? So you add those all up, and then, of course, like we do in calculus over and over again, we take it to the limit. I'm not going to sing it for you this time. And keep getting finer and finer, smaller and smaller shells until we get the actual volume, okay? But now, instead of using the area of a disk, we're going to use the volume of the shells and figure out what that formula looks like, okay? So what is the volume of a cylindrical shell? So on the next page, let's actually derive that for a given shell, okay? This cylindrical shell is the shape that I'm talking about, where you've got basically a tube with a certain radius on the outside and radius on the inside, and the difference between the two radii, the width of the side itself, is what I'm going to call delta R. Okay? So the volume will be the outer cylinder minus the inner cylinder. And you understand what I mean by outer and inner, right? So you've got the outer radius, and then you've got a smaller radius inside that I'm just cutting out of it. Now, what's the volume of a cylinder?
Pi r squared h.
Yep. It's the area of the base, which is pi r squared, times the height. So, pi, and the outer one is r2 squared, right? You see that's what I've got drawn right there. The radius all the way to the outside. And then times h minus pi r1 squared h. By the same rationale, this is now the inner radius. Now, I can stop right there, but it makes it complicated to try to do the calculus later on. What I'm actually going to do here is I would prefer to write this in terms of delta r and this r, which is the average radius between the two. And I didn't come up with this idea, so I'm not telling you so much why we do this, other than it gets us where we want to be, where we have a nice formula at the end. So somebody smarter than me came up with this, but it makes sense to me. So I'm going to explain it to how it makes sense to me. First of all, factor out the pi and the h from both of those.
You said r is the average radius?
This r over here, yes. So it would be, if this inside one is r1 and the outside one is r2, then r is right in between them. In fact, it'd be like r is r1 plus r2 over 2. It's the average of the two. So if I factor out the pi h, I'm left with r2 squared minus r1 squared. And here's where somebody got creative. They factor the difference of squares. You have r2 plus r1 and r2 minus r1. Right? Because the difference of squares is just r plus, a squared minus b squared is a plus b, a minus b. And the last creative step that they went through and did was to make this into the average, like I have up here, r1 plus r2 over 2, by dividing by 2. But you can't just stick a 2 in without pulling a 2 out, so we'll put a 2 out here. Notice I've just multiplied by 2 over 2 now. And by the way, what is R2 minus R1? What's the difference of the two radii?
Delta.
It's the delta arc, right? So I can write this as 2 pi h r delta r. That's the volume of a given cylindrical shell. Now when we're actually going to do this, like up above, whenever we divide up the interval from A to B, and we pick an x in there, and then we're going to do a whole bunch of different x's, like these 5 intervals there. We're going to have these different cylindrical shells. Notice in practice what that means is the width here is now going to be a delta x, right? Because it's going to be, we've broken up the x-axis into these pieces, and then the height is right here. It's the function height. So instead of having 2 pi h r delta r, we've now got 2 pi. The height is f of x. The r is the actual distance x. So I've got x f of x delta x. 2 pi x f of x delta x. Right? Because, again, r is now x, delta r is now delta x, and h is now f of x. So if you take all of those and plug them in, that's what you get for the volume. And then the next step beyond that is to say we're going to do that for every single one of those different shells. So you actually have a volume for each shell, and so this is going to be xi star, and this is xi star. And the reason I like to go ahead and put the xi stars in there is because in a minute I'm going to write it with a sum in front of it, and then have this formula that have xi stars in it, delta x. And if you take that to the limit, that is the very definition of a definite integral. So now I can replace the limit of the sum with just the integral symbol. Okay? And so what I'll then have is basically I've got to remember this formula. Instead of pi times the outer radius squared minus pi times the inner radius squared, that's what you did for the disk and the washer method. Now what you're going to do is you're going to find the cylindrical shells, and you're going to do 2 pi x f of x dx. Okay, so let's formally write this out now then. Let's say we've got a solid S that's obtained by rotating about the y-axis some region bounded by y equals f of x. And we are assuming, by the way, f of x is positive here. Bounded by y equals 0, so from, the x-axis over the range from a to b. Then we divide that interval a to b into n sub-intervals of equal width, all delta x. We call xi the midpoint of the ith subinterval. And so your volume is approximately equal to the sum of all those cylindrical shells. I equals 1 to n of 2 pi x I bar f of x I bar delta x. And then we take the limit. And so the volume is formally the limit as n goes to infinity, the sum from I equals 1 to n of 2 pi xi bar. That I just introduced the bar notation to emphasize the fact that it's a midpoint. That's a common way to indicate something is the average, is by putting a bar over the top. If you take in statistics, you'll recognize that that's the average of a data set. And then delta x. But the difference between using that and I star. Xi star always meant just choose any point out of that interval and use it. Now I'm choosing a specific point. It still works in that this is now, by definition, the limit from A to B of 2 pi x f of x dx. So this is the formula I went ahead and put in the box on the next page. That's the one you need to know, because that's what you're going to use to actually find the volume. So everything so far here is explanation as to why we use that formula, where it comes from. I do want to point out before I flip to the next page, to me, one easy way to see why that formula makes sense, the 2 pi x f of x as a volume for a cylindrical shell, comes from this picture. If you slice this shell and unroll it, it's very similar, especially for small delta x, to this rectangular box, right? The length around the outside of a circle is 2 pi r. That's the circumference of a circle, which is why the bottom side down here I have is 2 pi x. And then the height, of course, is just f of x, and the width is delta x by definition here. So the volume of this is, in fact, 2 pi x f of x delta x. So it tells us, that's what this geometric picture down here kind of explains, is that this formula makes sense. Even though I did some weird algebraic trickery to get there, it makes sense that that would be what the volume of that shell looks like. And then when you add up a whole bunch of shells together and take the limit, you end up with this derivative. So you remember 2 pi x f of x dx. And if you want to remember that in your head, remember it from this rectangular box that you get from unfolding the shells. Okay? So let's go back and find the volume of the solid we were looking at before, using now our new method of cylindrical shells instead of using the washer method. Okay, so remember the picture looks like this. So I'm going to revolve this around the y-axis. So I'm going to choose an x in between here, and I'm going to go up to that height. You get this little rectangle that's now going to be the edge of a shell that's going around. I'm not going to draw the whole thing. I'm just going to draw the one shell for now. But you don't even have to draw the shell to be able to do this, because once you recognize that it's a volume by a cylindrical shell, you know you're going to use the integral formula for cylindrical shells. F of x now is 2x squared minus x cubed dx.
This on definite or indefinite?
Well, we're finding an area, so we need a numerical value out of this. So the question now becomes, what are the limits? Okay, so what is the range of the x's over which this thing can move? Since it starts at the origin and moves up, I know it starts at 0, but the question is, how far out does that go? Because I didn't give that to you. How would you figure that out? Okay, so graph it, use your trace on like a graphing calculator, that would work. Can you do it analytically?
Yeah.
How?
No idea.
Well, what's the height of the curve at this point?
0.
0. What's the equation for the curve? Yeah, set it equal to 0 and solve. Okay? Factor out the common factor of x squared 2 minus x. When you have a product equal to 0, you use the property, the 0 property rule says If two things multiply together to give you 0, then either one can be 0. So x could be 0. Actually, x squared could be 0, which means x is 0. Or 2 minus x could be 0, which means x is 2. Okay? So you can do it from the graph. I don't have an objection to that, but you can also do it directly, analytically, and know that this goes from 0 to 2. And the rest is Cal 1. So far, I've given you a bunch of easy integrals. I'll give you a couple of more interesting ones by the end of this lecture. I would multiply this out. In fact, well, I don't know. Pull the 2 pi out. I'll leave the 2 pi in. Who cares? How about 2 pi x cubed minus 2 pi x to the 4th. I'm going to integrate that from 0 to 2 dx. You with me so far? Oh, that's 4. Yeah, 4. You're not with me. Correctly so. 4 pi x cubed minus 2 pi x to the 4th. Pi x to the 4th. Because you raise that to 1 and divide by it. X to the 4th over 4. The 4's cancel. 2 pi x to the 5th over 5. From 0 to 2. So plugging in 2 gives me pi 2 to the 4th minus 2 pi 2 to the 5th over 5 minus 0. So 16 pi minus 64 pi over 5. So that's what, 80 over 5? So 16 pi over 5. Now we'll talk a little bit more about this in a moment, but on at least a couple problems in your homework, you'll have to decide whether the cylindrical shell method works best or the washer method works best. And it's a decision between, am I going to slice it one way or slice it another way, right? If I slice it one way and create circular regions, but I'm going from the same function to the other function, you don't want to use the disk method or the washer method. You want to use this. So you slice it the other way and then just set up the formula straight from that box, number 2, that I got right there in front of you, okay? There are times where you can do either one and it works both ways. And the integral one way is easy to integrate. And the integral the other way is not, okay? Where one substitution pops out and it works perfectly, the other one you can't even integrate. So that's another way to decide which method to use, is that if you use one method, you can't even do the integral. For the other method, you can. Okay? So when revolving these things, generally you can use either one. It's just whether or not either you're going from the same function to the other one or the integration becomes too much of a problem. So this one actually tells you, in fact, several of the ones in your homework will say, use shells to do this. It may not even require that you use shells. That is, you could probably do it by the disk method or the washer method, but it's telling you do it by the shell method. So we're going to find the volume obtained by rotating about the x-axis, the region under the curve, y equals square root of x from 0 to 1. So step 1, draw a picture. Rotating about the x-axis. The curve y equals square root of x, for x goes from 0 to 1. That's like x equals y squared. So it's like a parabola, but it's on its side, right? So it actually ends up looking like a sideways parabola like that. And only the top half of it. Okay, so we're rotating it around the x-axis, so it's a sideways bowl, right? Okay, but this says use the shell method instead of the disk method. Now, how do you tell which one's which? Well, think of it in terms of where you're slicing. Am I slicing the x-axis or am I slicing the y-axis? Notice if I came here and I sliced right here, right, on the x-axis, and cut it, what shape do I get? I get discs, right? On the other hand, if I slice it this way, I get that little rectangular sliver that would then, when you rotate it around, gives you the shell. Okay? So, I am going to be slicing this way. Say, I'm going to pick a Y, and then draw my little box there. And so this is now a little bit trickier. It's still going to be that 2 pi variable times the function formula. But you got to remember that in that formula, when you have the integral of 2 pi something times something d something, right? This is your variable. This is your height of the shell, and that's the same variable. So in this case, my volume is going to be the integral of 2 pi y. Now, why is the variable y? Because I cut it on the y-axis. And now what's this height right here? That's what I've got to put into the f of x part of that formula. Okay, so a y is equal to square root of x is the way you would get the height of the function if you had an x. But that means I can solve this thing for x and get y squared. But where is y squared on this? That's this distance to right there, right? So that's y squared. That's this distance here. You see what I'm saying? X equals y squared is that distance horizontally. I don't know if you can see my dot moving right there, but it's this distance here. But I want to know this. Because that's 1, and if this is y squared, then the distance here is 1 minus y squared. That's what I'm going to put in right here. So 2 pi, this variable, times the height of that box, dy. And that's as tricky as it gets, really. It's not just necessarily the function itself.
So if it said from 0 to 5, it'd be 5 minus?
Yeah, because it's however far it is to that end. Okay? Now there's actually a second shape, and I'm not going to draw this on the paper. It actually literally said in the problem, the area under the curve y equals square root of x, right? Which happened to be this area right here. Rotated around to make that bowl-looking shape. Okay? On the other hand, I could have asked a completely different question with the same curve. And I could have said, what is the volume that you get when you rotate about still the x-axis for x equals y squared, the area to the left of that curve? What if I had said, let's take this area and revolve it around the x-axis. Okay? This one, whenever I chose a y, I had to find 2 pi y, the length of this box. But if I had said take this one and rotate it around and find its volume, I would have to pick a y, and now it's just the length of that box, right? Over here, it's integral 2 pi y 1 minus y squared. And over here, it's the integral 2 pi y times just y squared. See how the problem can vary? It's all about how tall is your cylindrical shell. And like Kaylin pointed out, this one happened to be because I can figure out this distance is y squared. Whatever this endpoint is here, 1 minus that curve. Okay? Whereas this one, it's just that distance from the axis out to that curve as a function of y. Okay. What are the limits? What's the range over which this y can slide? 0 to 1. So that's integral 0 to 1, 2 pi y minus 2 pi y cubed dy. Which is equal to pi y squared minus, I think, pi y to the 4th over 2, because it's 4 and the 4 cancels with the 2, from 0 to 1. Pi minus pi over 2, plugging in 1 for each of the y's, and then plugging in 0 gives me 0, so I get just pi over 2, I believe. Now this one's actually just as easy as the first one that I did. I only throw it in because it's got substitution shows up in the integration. I want to remind you of seeing that. And then I can use it to make the case of why sometimes it's easy one way and hard the other way. Let me point out what the shape of this curve looks like. So first we draw the shape. E to the x squared, actually if you plug in x equals 0, you're at 1. And then if you go over 1, you're at a height of e. Because you just plug in 1, you get e to the first. And it's shaped like an exponential curve, only a little bit sharper. It bends more than a standard e to the x. But you can get that from graphing it. It says compute the volume generated by rotating that function about the x-axis. Now what I want to do is the volume under the curve about the y-axis. Yeah, I think I said x-axis. So under the curve means I'm taking this region down here, right? And I'm going this way with it. So let's again think about what would be the best way to do this, washers or discs. So if I do, if I slice on this axis, right, and this thing is revolved around the y-axis, I'm going to get washers or discs. Okay, and in fact, the reason why I don't like that method on this one is from here up to here, that is from 0 to 1 on the y-axis, anywhere that I slice here, here, or here, right? I'm going to get solid discs. And then when I get up here, I'm going to get washers. So it changes. It's two different problems. It's just a solid cylinder from 0 to 1, and then it's a washer method from 1 to E, right? I could do it that way. In fact, I'll get the same answer if I just added those two volumes up. But it would be easier to do this as just one integral, because if I do it vertically and do a whole bunch of these boxes, notice as I go from 0 to 1, it's just a bunch of shells, all going from the same bottom up to the same function. So I'm going to use cylindrical shells. And it's the easiest kind of cylindrical shell problem, going from the axis up to the function. So the volume is immediately integral of 2 pi x e to the x squared dx. 2 pi times the variable, right, that you've chosen, the height of the box, which is e to the x squared, and the integral just goes from 0 to 1. Okay, so how do we integrate that? It's not as easy as the ones we've been doing, which have all been polynomials. Okay. Problem is you got x in there, you've got e to the x squared. Remember, there's no product rule, so you can't integrate the first part times the second part. Use substitution. What would you let u be? If you use e to the x squared, then your your du is going to have an e back in it, and then you need two e's. So if you just use x squared, then du has the 2x dx. Right? And notice that's already in there for me. There's the 2, there's the x, there's the dx, so there's du, and then here's e to the u. I got rid of all my x's. So this volume becomes the integral of pi still there, e to the u, du. I've changed the integrand. I've changed the differential. When you're doing definite integrals, you got to change three things. What else are you going to change? Limits. So how do you change the limits? You plug them into your substitution. So u at x equals 0 is 0 squared, or 0, and u at x equals 1 is 1 squared, which is 1. So actually the limits don't even change in this case. So pi e to the u from 0 to 1. Right, the integral of pi e to the u is pi e to the u. So you get pi e minus, that's e to the first, minus pi e to the 0, which is just 1, or pi times e minus 1. Now, actually, this is not the question I wanted to ask. I meant not to ask this one. So you can mark that up. In fact, I don't want to even discuss that. I think we're fine in seeing that example and moving on from there. Okay? So that's our new method, the cylindrical shells. I threw this problem in here at the end just for your own personal challenge. I'm not going to do this, although I will probably in the next couple of days post a solution to this just so you can see this. I thought it was an interesting problem that can be solved using cylindrical shells. And it's a kind of a surprising result, at least in my opinion, whenever you actually do this. These things are napkin rings. You've seen napkin rings. Like you just throw a napkin through the middle of this, cloth napkin, not your Taco Bell level of dining, but a little bit higher level than that. fine dining that involves cloth napkins. Now, you've been to Olive Garden; they have cloth napkins, so that works. But they may not have wooden napkin rings. What they did was they took a sphere and they just drilled a hole through the sphere. And they did this for two different rings. It just so happened that the spheres were different diameters, or different radii, and the size of the hole was different, but it was done in such a way that the height ended up being the same. And so the question is, which one of those two rings has more wood in it? And so you guess. Then you go back and you calculate using cylindrical shells. And what I mean by using cylindrical shells on this example would be, set the problem up where you've got a three-dimensional problem. So you're basically taking this curve right here, right, and rotating it, or this area here, and rotating that about the y-axis. So this curve would be defined by x squared plus y squared equals, say, radius 1 squared. And so you'd pick whatever your starting radius is here out to the actual end of the radius and build your cylindrical shells this way. And revolve those around and get the integral and see what you get. And then do the same thing on this one, only you've got a different starting radius. So you've got a different value for there and a different radius for your sphere here. And then do the same integral on that one, x squared plus y squared equals little r2 squared. And do that same cylindrical shell method and try to find the volume of that guy by revolving this particular area around the y-axis. And see which one actually has more wood in it, you can tell. Okay? All right, that's all I've got, so I'm going to stop there. The 6.3 homework is already available, so you should be able to get on there and start working on it. It is due on Wednesday, so be sure you take a look at it, and if you have any questions, click the button or come see me.